All right, so we're going to start off with chapter 8 by talking about symmetric matrices. And what you're going to notice is that symmetric matrices actually give us a lot of really nice results, which is going to lead to probably one of my, if not the favorite theorem throughout this whole class. It's one of my favorite, but I'm willing to bet it's like up there with one of my favorites. So with that said, let's kind of start off by making some comments as to what we're interested in. So in this section, we are interested in the matrices A in which there exists an orthogonal matrix matrix S, or if better, I mean, if we have an orthonormal, even better, because so maybe in parentheses I should say an orthogonal or orthonormal, right? Because we know orthonormal matrices have nice results, also because the vectors are unit vectors, so we get some nice results out of that as well. So matrix S such that S inverse AS equals to S transpose AS. And if you remember, we're going to use this idea, and we know that in chapter 5 of this book we talked about, hey, if we have an orthogonal matrix, we know that S inverse equals to S transpose, as long as what? If S is orthogonal, right? So we discussed this in chapter 5, so that we already know. And what we want to show that such that this, more importantly, is diagonal. So in other words, we're trying to say, hey, for instance, what are my matrices that are orthogonally diagonalizable? And what is it that we mean? If we grab this product here, what we'll notice is it'll give us a diagonal matrix in return. And we know that when we have diagonal matrices, there's a lot of nice results we can get out of it. There's a lot of things we could do. For instance, one example of many would be if I have a diagonal matrix and I say, hey, what's the this matrix multiplied to itself 10 times, or this matrix to the power of 10. You just end up taking the diagonal entries and taking it to the power of 10. So it's a nice way, rather than using the exhaustive method of multiplying matrices out. So with that said, let's start off with our first example. So, and this is kind of like the one-way proof of my favorite theorem, which we're going to get into afterwards. So we're going to say, look, if A is orthogonally diagonalizable, the question is, what is the relationship between A transpose and A? Okay, so we're actually going to notice something really nice happens. So what is it that we know? We're assuming that, look, A is orthogonally diagonalizable. Okay, so what does that mean? If it's orthogonally diagonalizable, so let's just kind of go one step at a time. We could say, look, since A is diagonalizable, this implies, what is it that we know? We know that there is a matrix S where S inverse AS, and this matrix S that we're talking about is obviously invertible, where that gives me a diagonal matrix, right? And more importantly, what is it that we know about this matrix S? Not only is it invertible, it's an orthogonal matrix, right? So we know that this matrix is invertible, and it's orthogonal as well. So here's what what does this imply? If that's the case, then we know that matrix A could be written as S d S inverse, right? Because obviously if it's invertible, then I could solve for matrix A here. Okay, so that's what we have. So why is it that I care about A? Because what is it that I'm trying to do here? I'm trying to compare A transpose with A. So we know that if A is diagonalizable, there exists an invertible matrix S such that S inverse AS gives me a diagonal matrix, which means A is the same thing as S times the diagonal matrix times S inverse. Okay, so now getting to answer our question, now we're going to say, well, so A transpose is the same thing as what? S d S inverse transpose, which before I kind of simplify this, what is it that we know? So this turns into the same thing as S d S transpose. Now, what's my justification from this step to this step is because we know that since S is orthogonal, we can do that. Okay, so if that's the case, then we know that from the properties of transpositive matrices, this becomes the same thing as what? S d transpose S transpose. All right, and then what is it that we know about diagonal matrix? Since D is diagonal, the transpose of a diagonal is just itself. So what is it that we get in return? We get S d S transpose. Okay, so from here to here, all I did is I said, look, the transpose of a diagonal matrix is the matrix itself. So what is it that you notice here? What is it that we got in return here? Well, let's kind of take it a step further. So what is it that we know about S d S transpose? That's the same thing as S d S inverse. Now, why am I doing this? I'm trying to kind of make this clearer. Now, how come I could go back to this? Because once again, S is an orthogonal matrix, so S transpose is the same thing as S inverse. Now, what do you notice about S d S inverse? What do we show up here? That's the same thing as A. So this equals to A. So what is it that we noticed here? What does this imply? What happens when you take a transpose of a matrix and get itself back? That implies that A is symmetric. So we actually proved something really nice here. And what is it that we proved? We said, look, if we have an orthogonally diagonalizable matrix, then that matrix itself must be symmetric. So which is going to get into the theorem, this important theorem that I'm talking about. So this was the one-way proof of it, and you'll see what I mean in a minute. So this, showing that A became a symmetric matrix because it was orthogonally diagonalizable, now gets us to the spectral theorem, which is, like I said, my favorite theorem that we're going to work with in this school year. So we could say that a matrix is orthogonally diagonalizable. So when we say a matrix is orthogonally diagonalizable, what is it that we mean? For instance, there exists an orthogonal matrix S such that S inverse AS equals to S transpose AS, which this is diagonal. Right, so if we multiply this out, we're going to get a diagonal. So if we say A is a matrix is orthogonally diagonalizable, that's basically what we're saying, right? I could find a matrix S where S inverse AS or S transpose AS is a diagonal matrix, okay, if and only if A is symmetric. So this is actually really cool the way it works, right? So we're saying A transpose equals to A. So in other words, what is it that we're saying here? What is it that we're claiming here? We're claiming, which we pretty much proved. See, this is an if and only if statement. So we've proven it one way, and the other way we could also prove itself. But this was the more interesting part that we proved. But all we're saying here is what? We're saying, look, if you have a symmetric matrix, then it's orthogonally diagonalizable. And then obviously the other way is also true. We're saying if we have a matrix that's orthogonally diagonalizable, then the matrix must be symmetric. So this really cool result is saying what? Anytime you have a symmetric matrix, guess what? it's orthogonally diagonalizable. It's guaranteed to be orthogonally diagonalizable. So let's do our second example where we'll see kind of this in play. And we'll put the spectral theorem to use. And you'll notice, and by the way, we'll put the spectral theorem to use over and over and over, even in sections to come. Because look, right now, what is it that we're noticing here? I have a matrix, and for it to be symmetric, it has to be square. So the question is going to be, well, what if it's not a square matrix? We're going to do some really interesting things in the future where we're going to force matrices that aren't square to become square, and then in the process of doing so, we happen to make them symmetric as well, which once they're symmetric, boom, we could use the spectral theorem. So you'll see how this kind of comes into play, okay? And hopefully by the end of the school year, you'll agree with me that the spectral theorem is one of the coolest things you're going to see, okay? So let's go on to the second example. So for the symmetric matrix A, which is defined as 3, 2, 2, 3, find an orthogonal matrix S such that S inverse AS is diagonal. Okay. So what's going to happen now is, now you're going to say, okay, well, we know that this is a symmetrical matrix S, matrix A, so we know that this should be diagonalizable, but now the question becomes, how do I go about diagonalizing this? Because we know that we can start off with finding S in a way where it has to be invertible. So if we think back to last chapter, see, here's what we know. If the matrix S, we need to find a matrix S that's diagonalizable, what is it that we can do? We can go after eigenvectors, because what is it that we know? The eigenvectors can help me find an eigenbasis. And if I could find an eigenbasis for this guy, and what is it that we know? We know that since this is diagonalizable, it should have an eigenbasis. And see, from last chapter, we found nice, effective ways of finding eigenbases without really running into any problems. And then, once we find the eigenbasis, we're going to notice we get a really nice result out of this, which is going to get us into the next theorem. So let's start off by saying, okay, you want me to find this matrix S. Let's not worry about the orthogonal. Let's first find the matrix S that is invertible, and then we'll make it orthogonal, but you'll see what will happen. So we're going to say, okay, look, to find this matrix S that's invertible, let's find the eigenbasis, because we know that the eigenbasis, after all, it is a basis, it will be linearly it will form a matrix that's invertible because all my vectors are linearly independent. So how do we find the eigenbasis? Well, we first need to find our eigenvalues. So to find the eigenvalues, we're going to say the determinant of 3 minus lambda 2, 2, 3 minus lambda has to equal to 0, which implies, what is this going to be? 3 minus lambda squared minus 4 equals to 0, which implies, if you simplify this, we get 9 minus 6 lambda plus lambda squared minus 4 equals to 0, which becomes lambda squared minus 6 lambda plus 5 equals to 0, which this factors to lambda minus 5. Lambda minus 1 equals to 0, and then I get lambda sub 1 is 5. Lambda sub 2 is 1. Okay, so now that we found that, let me actually move this up so we could continue. Okay, so if that's what we have. So now that we have our eigenvalues, now we're going to go after finding our eigenspace for each eigenvalue. So the eigenspace for 5, that's what? Literally the kernel of, what does this become? It'll be negative 2, 2, 2, negative 2. And what is it that we notice? The kernel of this, we can just see it. What would that be? These are exact opposites. So what is it that we need? Just 1, 1. Is that correct? That's right. So what is it that we know? Our eigenspace for lambda 5 is just a span of 1, 1. Okay? So how about the eigenspace for 1, for lambda of 1, or the eigenvalue of 1? That's just going to be the kernel of 2, 2, 2, 2. Which, what do we know that they're exactly the same? So I could say, for instance, 1, negative 1. And so E sub 1 will be the span of 1, negative 1. Okay, so now we're going to notice something really nice happening here. So we're going to say, look, notice that E sub 5, the eigenspace of 5, and the eigenspace of 1, they are perpendicular. And sure enough, look at how come they're perpendicular. Dot them together. What's 1, 1 dotted with 1, negative 1? It becomes 0. So what happened is we noticed that, look, these are linearly independent. So these are the vectors I'm going to use to construct S. But we automatically got something that they're not only are they linearly independent, but they also end up being orthogonal to one another. So it's kind of like the matrix I'm creating here is becoming an orthogonally diagonalizable matrix, or S is already an orthogonal matrix to begin with. So I didn't have to go beyond what I did here. Now, is that a coincidence? The good news is it's not. So we'll actually talk about that and prove it as well. So we can say this. So if these are perpendicular, then we can find an orthonormal eigenbasis. Now, making it orthonormal should not be difficult, right? Because all we need to do is turn these into unit vectors, and then later on we'll start seeing the importance of this. So here's what we're going to say. V sub 1, which will be 1 over rat 2, 1, 1, and V sub 2 will be 1 over rat 2, 1, negative 1, right? So I just made them into unit vectors. So what's S going to be? My matrix S, which we're looking for anyway, is 1 over rat 2, 1, 1, 1, negative 1. And sure enough, I'll let you do the math on your own, but here's what's going to happen. S inverse AS is going to result in 5, 0, 0, 1, which we shouldn't be surprised with this, because what are these? These are my eigenvalues, right? They're just being filled with my eigenvalues. But if you want to verify this, you could. But we finished this up. We found the matrix S here. Now, that was an orthogonal matrix, and in this case it was orthonormal, where when I found its, when I diagonalized it, I found a diagonal matrix which was filled with my eigenvalues, which shouldn't be of any surprise because we saw that last chapter. Okay, so with that said, now let's continue with the next theorem, which is theorem 8.1.2, which says the following. Consider a symmetric matrix A if V sub 1 and V sub 2 are eigenvectors of A with distinct eigenvalues lambda sub 1 and lambda sub 2, then lambda sub, or sorry, not lambda sub 1, then V sub 1 dotted with V sub 2 equals 0. And so what is this theorem saying? Look, if we find our eigenvectors and they come from distinct eigenvalues, then when you take their dot product, they'll be 0, which means that is what? They're going to be orthogonal. So that is V sub 2 is orthogonal to V sub 1, which is a really, really nice result. So here's what we know. If we go after our eigenvectors, if they come from distinct eigenvalues, those eigenvectors are guaranteed to be orthogonal to each other. So the last example that we did, notice our eigenvalues were what? 1 and 5, which clearly they were distinct, and the eigenvectors that I found happened to be, or they ended up being orthogonal, which wasn't a coincidence because this theorem is stating that. So with that said, we're going to prove this because this is actually a really, really interesting result, and so we definitely want to prove this and show it. So the only time that our eigenvectors will not be orthogonal possibly is if they're in the same eigen space, right? So then we would need to turn them into orthogonal, which that we know, right, because of the Gram-Schmidt process. That was the whole purpose of the Gram-Schmidt process. So let's prove that theorem, which is a really, really nice result. So, and this proof is actually interesting the way it works also. So hopefully you could follow along with this. So here's what we want to do. We want to show that. So we're going to take taking the product. V sub 1 transpose A V sub 2. Okay? So what am I doing here? What I want to try to show here is that somehow I want to turn this into the dot product. Now, why am I doing this? And by the way, we're assuming, so let's just say suppose V sub 1 and V sub 2 are eigenvectors of matrix A. Okay, so that's kind of the assumption we're going off of, right? So we have this assumption, so we're going to take the product of V sub 1 T, transpose of V sub 1, and we want to multiply it into A V sub 2. Now, if you remember, this is using matrix multiplication of vectors, right? Because I can take either dot product of matrix, two vectors, and we know that A V sub 2, that in itself is a vector, right? So we know that we could either dot this, or we could use the idea of transpose to write this as a row vector multiplied by a column vector, which gives me this. Now, where am I headed with this? So you might say, okay, cool, you're taking this, but more importantly, what is it that we want to show? We want to show that the dot product of this is 0. So notice how there is no dot product yet, but this is done intentionally. So if we start off with this product, what is it that we can do? We could say, well, this is equivalent to what? V sub 1 transpose times lambda sub 2 V sub 2. Now, where did this come from? Lambda, remember, that's my eigenvalue, and what is it that we know? Since V sub 2 is an eigenvector of A, we know that from this step to this step, we know that A V sub 2 is equal to lambda sub 2 V sub 2. All right, so that's the transition I made. Now, with that said, now I could rewrite this as what? Since lambda sub 2 is a constant, I could just move that out front. Since this is a scalar, I could say that's V1 transpose times V sub 2. Or another way of expressing this is equivalent to what? Lambda sub 2 V sub 1 dotted with V sub 2, right? So it's kind of like this result and this result are exactly the same. Okay, so now I was able to connect this to the dot product between V sub 1 and V sub 2. Okay, so we're like halfway there. So here's what I'm going to do. I'm going to say also, going back to this original statement I made, I could say this is the same thing as V sub 1 transpose A V sub 2, right? So I'm starting off with this guy, right? So parentheses or no parentheses, it doesn't matter, right? So this is, I could say the same thing as that, right? That becomes the same thing as what? V sub 1 transpose A transpose V sub 2. Okay, so what am I basically doing from this step to this step? I'm just taking what? The transpose of A. And what is it that we know? A is symmetric, right? That's what our theorem was saying. So this is equivalent, right? So then, since I wrote this as a transpose, and I know that A is a symmetric matrix, then I could rewrite this as what? I could say this is the same thing as what? A V sub 1 transpose times V sub 2. Okay? Now, With that said, what do I know about A V sub 1 transpose? That's the same thing as, so we know that A V sub 1 would be the same thing as, once again, since V sub 1 is eigenvalue, we know that A V sub 1 is going to equal to, so we know that A V sub 1 is equal to lambda sub 1 V sub 1. So I'm going to use the idea of, or the definition of our eigenvectors with the associated eigenvalue. So this becomes lambda sub 1 V sub 1 transpose times V sub 2, which then, this, we know that a scalar's transpose is still the scalar itself. So what does this become? This becomes lambda sub 1 V sub 1 transpose times V sub 2, which is the same thing as what? Lambda sub 1 V sub 1 dotted with V sub 2. Okay? So what have I just shown here? So we know that I just showed that this is the same thing as that, right? Or, well, these two are clearly the same. And these two, this is V sub 1 transpose times A V sub 2 is the same thing as lambda sub 2 V sub 1 dotted with V sub 2. Also the same thing as lambda sub 1 V sub 1 dotted with V sub 2. So in other words, what is it that we just showed? We just showed that by doing all of this, lambda sub 1 V sub 1 dotted with V sub 2 is the same thing as what? Lambda sub 2 V sub 1 dotted with V sub 2. And since these are all scalars, right, so if I move this over to the other side, what does this imply? This implies we have lambda sub 1 minus lambda sub 2 V sub 1 dotted with V sub 2. So what I did was, so, and this equals to 0. So what I did was I took this over to the other side, and I factored a V sub 1 dotted with V sub 2, and I was left with lambda sub 1 minus lambda sub 2. So now, here's where we're going to put the proofs together and everything's going to make sense. So here's what we know. Since lambda sub 1 and lambda sub 2 are distinct, right, they're not the same, it's impossible for this guy to equal to 0, which, what does that imply? V sub 1 dotted with V sub 2 must equal to 0. So we're going to say since lambda sub 1 and lambda sub 2 are distinct, which means it's impossible, right? Lambda sub 1 does not equal to lambda sub 2. That's a fact. That's what was given to us, right? That was our assumption. This implies the only way this will equal to 0 is what? V sub 1 dotted with V sub 2 must be 0. It has to be 0, which completes our proof, because since this is 0, then we know that V sub 1 and V sub 2, our eigenvectors, are orthogonal to each other, right? So it's a lot to take in, a really, really cool proof and the way it works, but that's pretty much, that's guaranteeing us that, hey, anytime you find eigenvectors of distinct eigenvalues, you're guaranteed for them to be orthogonal, which we're starting to see the advantages of working with eigenvectors. And of course, the spectral theorem is going to have its advantages as well. So from chapter 7 and on, things get really, really interesting in this class. So let's move on to our next theorem. We won't prove this next theorem, but I'm pretty sure you could pretty much figure out how you would go about proving this. So this says a symmetric n by n matrix A has n real eigenvalues if they are counted with their algebraic multiplicities. Okay, so all this is saying is, look, if I have an n by n matrix, I'm going to have n real eigenvalues, right? Counting their algebraic multiplicity. So all my eigenvalues should be real, right? How come? Because if it's symmetric, we know it's going to be diagonalizable. So I should be able to find, you know, through this, you could use the spectral theorem to kind of to find all your your matrix S that is invertible, which means you should be able to find n linearly independent vectors. And each linearly independent vector is going to be an eigenvector, right? And each eigenvector is going to have an associated eigenvalue. So we're going to have n real eigenvalues. So that's obviously for symmetric matrices, which the proof of this is going to put the spectral theorem's idea to use. Okay, so just keep that in mind. So moving on to the next theorem, which this next theorem is kind of like talking about, hey, how do we orthogonally diagonalize a matrix, which it's kind of like stating out the steps for us, which we could already pretty much figure out how to do this. So let's talk about this theorem, which this says orthogonal diagonalization of a symmetric matrix A. So these are kind of like the steps, and I'm sure you can guess. So if I gave you a symmetric matrix and said, hey, orthogonally diagonalize this, what's the first thing you'd do? Well, you would find the eigenvalues of matrix A. And then once you do that and find the basis of each Eigen Space. Okay, so then after this, part B might be necessary or it might not, right? So this depends on how many distinct eigenvalues we have. But if I have more than 2 vectors in each eigenspace, then I may need to make them orthogonal to each other. We know that all the other eigenvectors for the non-distinct eigenvalues, they're going to be orthogonal to each other. It's just the ones that are in the same eigenspace, I would need to turn them into, make them orthogonal to one another, and we know how to do that, which is the Gram-Schmidt process. So part B, if we have more than one eigenvector in an eigenspace, then we need to make them orthogonal by using the Gram-Schmidt process. So using the Gram-Schmidt process, find an orthonormal basis of each eigenspace. Okay, so and then once we have that, once we've done part B, or if we skip part B, if we don't need to do this, then we can form our orthonormal eigenbasis. So we can form an orthonormal eigenbasis v sub 1 all the way to v sub n for A by concatenating by the orthogonal bases you found in part B. Or in other words, in fact, A and B, right? It's kind of like we're putting all the eigenvectors together. So, and S, what is S going to be? It's just going to be filled with all my eigenvectors. Okay, so there is S basically, right? So that's what's going on here. So we know that then once we do this, we know for a fact that S is orthogonal and S inverse AS will be diagonal. Okay, so that basically, this is the process, right? So and this shouldn't be anything out of the ordinary for us because we've dealt with all of these, right? So going on to our last example, which will end it here. So for example 3, we're gonna say consider an invertible symmetric matrix. So an invertible symmetric 2x2 matrix A. Okay, so we have our 2x2 symmetric matrix A. We're going to show that the linear transformation t of x, which is defined as ax, maps the unit circle into an ellipse. And find the length of the semi-major and semi-minor axes. Of the ellipse in terms of the eigenvalues of A. So we've done this before, but not in terms of eigenvalues. So we've actually shown that, hey, the linear transformation of a circle, the image is an ellipse, right? We've done that. But now we're going to actually notice that, hey, our eigenvalues can help us see more, and we can describe this ellipse in a better way. So here's what we know. So let's kind of start off with this. We know that since matrix A is symmetric, what is it that we're guaranteed? We know that we have an orthonormal eigenbasis for this. So, and that's the beauty of this. So we're going to use the spectral theorem. So we're going to say, look, by the spectral theorem, since our matrix is symmetric, then there exists an orthonormal eigenbasis v sub 1 and v sub 2 for t with associated eigenvalues. Let's call them lambda sub 1 and lambda sub 2. And we know for a fact that lambda sub 1 and lambda sub 2, we know that these guys are non-zero, right? Because what is it that, why are they non-zero? Let's think about it. Because if any of these eigenvalues are 0, what does that mean about the determinant of A? The determinant of A will be 0, and therefore it will not be invertible. So we know that lambda sub 1 and lambda sub 2 must be non-zero. Okay, so now we're also going to make an assumption. We're going to say, look, take the absolute value of lambda sub 1 to be greater than or equal to the absolute value of lambda sub 2. So this is just to say, hey, look, let's just assume that lambda sub 1 has the larger magnitude. That's all we're doing here, right? We don't have to, right? We could have also switched it around the other way, but you'll notice there's a reason why we're doing this, because then the semi-major and semi-minor axes, it'll be easier to see which ones they are, okay? So, and if now let's kind of go back to, hey, now what is it that I want to do? I want to run a unit circle through this linear transformation, okay? So we know that these are my eigenvectors, right? And this is, and they create my eigenbasis. So here's what we know though. We know that the unit circle consists of all vectors v equals to cosine of t times v sub 1 plus sine of t times v sub 2. Okay, and I'm not sure if you remember this, but we showed this earlier on in the year, how if I take all vectors that take cosine of t v sub 1 plus sine of t v sub 2. Now what do I know about v sub 1 and v sub 2? They're orthogonal, they're unit vectors, and more importantly, they're linearly independent. So if I take any multiple of these guys, or any scalar times these, and I add them together, more importantly, the magnitude of this is always going to be 1. That's going to give me all the points that land away from the origin that have a magnitude of 1, which creates my circle. But if you're not sure, if you want me to explain this again, just make sure to reach out to me and I will. So, and we know that v sub 1 and v sub 2 are an orthonormal basis. Okay, so with that said, now let's talk about the image. So here's my unit circle, right, which has to do with, I was able to write it in terms of v sub 1 and v sub 2. So here's the part where things get really nice and clean. So the image t of v, which is the same thing as what? T of, we said v is cosine of t v sub 1 plus sine of t v sub 2. That is the same thing as what? T of cosine of t v sub 1 plus t of sine of t v sub 2. Now what is it that we know about this? How did I get from here to here? Because it's a linear transformation. And then this is also the same thing as what? Cosine of t times t of v sub 1. Now remember, why am I able to times sine of t times t of v sub 2. Now why was I able to pull out the cosine and sine? Because remember, these are scalars, right? Those are just my scalars. So, and once again, since it's linear, the scalars can pull out up front. So with that said, what is t of v sub 1? That becomes cosine of t a v sub 1 plus sine of t a v sub 2, which, what's a v sub 1? That just becomes cosine of t lambda 1 v sub 1 plus sine of t lambda sub 2 v sub 2, which, what is it that we notice here now? I have, see, cosine of t v sub 1 plus sine of t v sub 2, that's my unit circle. But with the lambda sub 1, lambda sub 2, which these are scalars, what is it that I'm doing now? Now I'm stretching the unit circle in the v sub 1's direction by a factor of lambda sub 1, and I'm stretching the unit circle in v sub 2's direction by a factor of lambda sub 2. So we could see that what is an ellipse? It's just literally a circle, but one side is stretched out more than the other, or so on. There's more of a stretching factor, which, what is it that we notice? This is an ellipse, right? So this implies this is an ellipse. And what's the major axis? What's the semi-major axis? Well, it's the side that we stretch out more, which the lambda sub 1, and hopefully you could see why we made that assumption earlier on. So since we assume that the lambda sub 1 has the larger magnitude, that's going to be my semi-major axis. And the lambda sub 2, since that has the smaller magnitude, that's going to be my semi-minor axis. So this, we showed that the circle, the unit circle, when I ran it through this, the image became an ellipse. And more importantly, so this is an ellipse with semi-major axis of the magnitude of lambda sub 1 v sub 1. And what is it that I know here, by the way? Since v sub 1 is a unit vector, it just becomes what? The magnitude of lambda sub 1 and semi-minor axis, which would be the magnitude of lambda sub 2 v sub 2. And you're starting to see why it's nice if we have an orthonormal basis, or if I make my orthogonal matrix that we come up with, why it's better to make it orthonormal, which the magnitude of v sub 2 once again is 1, which just gives me the absolute value of lambda sub 2. So here's the cool thing. When we're talking strictly about circles to ellipses, my eigenvalues, my associated eigenvalues, will give you the length of the semi-major and semi-minor axis of your ellipse, right? So here's another kind of like an interesting application of eigenvalues, right? So we're starting to see how they are versatile in their own ways, right? So this pretty much takes care of section 1. Once again, if you have any questions, feel free to reach out to me. But this spectral theorem stuff, hopefully you find it as exciting as I do, because I personally love this stuff, and I really love working out problems that have to do with this. But once again, don't hesitate to reach out to me if you have any questions.